Installing mental model for TCP. Every time you load a web page, your data gets chopped into pieces, flung across the planet through dozens of machines that could drop it at any moment. And it arrives perfectly in order. How? It starts with a handshake. Before your computer sends a single byte of data, it has to introduce itself. Your machine sends a SYN packet, short for synchronize. It's saying, hey, I want to talk. The server responds with SYN ACK, synchronize acknowledged. It's saying, I hear you and I want to talk too. Your machine fires back one final ACK, acknowledged. And now both sides agree. We have a connection. 3 packets. No data yet. Just 2 machines making sure they can hear each other. This is the 3-way handshake, and every single TCP connection on the internet starts exactly like this. But here's the clever part. Those SYN and ACK packets aren't just saying hello. They're exchanging sequence numbers, random starting numbers that both sides will use to track every single byte that flows between them. Think of it like both sides agreeing on a numbering system before the conversation starts. Now the connection is open. Time to send some data. Say you're downloading an image. It's 100 kilobytes. TCP doesn't send that as one giant blob. It can't. Networks have a maximum packet size, usually around 1,500 bytes. So TCP slices your image into segments. Each segment gets a sequence number, not segment 1, segment 2. The actual byte offset. Segment 1 starts at byte 0. If it carries 1,400 bytes, the next segment starts at byte 1,400, then 2,800, and so on. Now here's where it gets interesting. These segments don't take the same path. One might go through Chicago, another through London. They arrive out of order. Segment 3 shows up first, then segment 1, then segment 5. But the receiver doesn't panic. It looks at the sequence numbers and slots each segment into the right position. Like puzzle pieces, they can arrive in any order, but the numbers tell you exactly where each one goes. And for every segment that arrives, the receiver sends back an ACK, an acknowledgement, with the sequence number of the next byte it expects. That ACK is a receipt. It's saying, I got everything up to here, send me what comes next. But what happens when a segment never arrives? The sender could just wait for an ACK after every single segment. Send one, wait, send one, wait. That would be perfectly reliable and painfully slow. You'd spend more time waiting for ACKs than actually sending data. So TCP uses a sliding window. The sender is allowed to have multiple segments in flight at the same time without waiting for each one to be acknowledged. Picture a row of segments lined up, ready to send. The window is a frame that sits over this row. Everything inside the window can be sent. Everything outside has to wait. Let's say the window size is 4. The sender fires off segments 1 through 4, all at once. As ACKs come back, the window slides forward. ACK for segment 1 arrives. The window shifts right, and segment 5 can now be sent. But watch what happens when a segment gets lost. Say segment 2 never arrives. The receiver keeps sending duplicate ACKs. ACK2, ACK2, ACK-2, because it's still waiting for that missing segment. After 3 duplicate ACKs, the sender doesn't wait for a timeout. It immediately retransmits the lost segment. This is called fast retransmit. The network itself is telling you something went wrong, and TCP listens. The window is the throttle. The receiver can also shrink the window to say, slow down, I'm overwhelmed. This is flow control. The receiver controls the pace. And it all happens through this one elegant mechanism, a frame that slides forward as data is confirmed. The sliding window controls how fast the receiver can handle data. But there's another bottleneck, the network itself. Routers between you and the server have limited buffers. If everyone blasts data at full speed, those buffers overflow and packets get dropped. The whole network grinds to a halt. So TCP doesn't just listen to the receiver. It also probes the network to find out how much it can handle. This is congestion control. It starts cautiously. TCP sends just 1 segment. If the ACK comes back, it doubles, 2 segments. ACK comes back, 4, then 8. This exponential growth is called slow start, even though it's actually pretty fast. But it can't keep doubling forever. Eventually, TCP hits a threshold and switches to linear growth. adding just one segment per round trip instead of doubling, cautiously feeling for the limit. Then, packet loss. A segment vanishes. TCP interprets this as congestion. The network is saying, you're sending too fast. So TCP cuts its sending rate in half, immediately. Then it starts climbing again. Linear growth, slowly pushing the limit, until another loss. Cut in half, climb again. This creates the famous TCP sawtooth, a zigzag pattern of growth and cuts that repeats forever. And here's the beautiful thing. Every TCP connection on the internet is doing this simultaneously. Millions of connections, all independently probing and backing off. And the result is a network that shares bandwidth fairly, without any central coordinator. No traffic cop, just math. The data is sent, every byte acknowledged, but the connection is still open. Both sides are still listening, still holding resources. Ports, memory, buffer space. On a busy server handling thousands of connections, those resources matter. So TCP needs a graceful goodbye. And just like the handshake, it's choreographed. The client sends a fin packet. I'm finished sending. The server ACKs it. Got it. But the server might still have data to send, so the connection is now half closed. The client is done, but the server isn't. When the server finishes, it sends its own fin. I'm done too. The client ACKs it. 4 packets, 2 fins, 2 ACKs. Both sides agreed to close. But there's one more twist. After sending that final ACK, the client doesn't immediately free the connection. It enters a time wait state, hanging around for up to 2 minutes. Why? Because if that last ACK got lost, the server would resend its fin, and the client needs to be there to re-ACK it. It's a safety net. TCP doesn't slam the door. It makes sure everyone got the message. From Handshake to Teardown, TCP gives you something remarkable. A reliable stream of bytes on top of a network that offers no guarantees. It slices your data, numbers every byte, retransmits what's lost, paces what's sent, and cleans up when it's done. All invisible, all in the background. Every time you load a page, stream a video, or send a message, TCP is the reason it just works. Cognitive architecture updated.